Namaskar and welcome back to another lecture in our series on development and applications of special concretes. We'll start today our discussion on anti-washout underwater concrete. It's a short discussion with basically photographs and a very broad outline of what this method and this concrete is all about. So getting started, this picture here shows a general view of the job site as you would see it in a large-scale underwater concreting operation. This picture here, on the other hand, shows the details, that is, divers working with, let's say, the reinforcement work. Now, this divers working with the reinforcement work brings to fore a very important issue relating to quality control. We have to the reliance on the last worker on the line, the divers in this case, to ensure a proper quality control, to make sure that the kind of reinforcement time that should be done has actually been done, becomes a lot more important in the case of such special constructions, because multiple layers of inspections and re-inspections, which is possibly easier in a normal environment, is not possible when we are trying to do construction underwater. Keep that in mind when we are working with specifications, trying to do the construction work and do quality control as far as such constructions are concerned. Moving forward, this picture, in fact the last picture, probably puts in better perspective what we were trying to do the last time when we looked at this picture. What we said here was that the testing for fresh concrete and the collection of cubes as far as strength is concerned for such concretes, underwater concrete, should be carried out underwater itself. That is, the concrete should be allowed to deform underwater and the cubes should be demolded and allowed to remain there, because that is what is expected of that concrete. As far as the water tank is concerned, yes, there are other specifications which need to be worked out. What should be the height of this water tank? Whether the water that we use here can be normal water, or it should be seawater, or it can be, let's say, artificial seawater. There is a specification which tells us how to make artificial seawater. What is the chemical composition that you should use if you want to make artificial seawater? Try to understand that. Try to look for literature and identify the specification and the composition. And of course, you can compare it with the natural seawater. So these are things which are left out from the scope of this discussion, where we are saying that, okay, so long as we understand the principle that the test should be carried out underwater, the detailed part of it, whether it should be salt water or it should be normal water, that can be worked out as far as individual specifications are concerned or the test methods are concerned. So I would encourage you to read some of the test methods relating to underwater concrete and find out what they have to say about the nature of water to be used in this water tank. Moving forward, this is another picture where concrete is almost being placed, and we can see that placement of high quality underwater concrete leaves the marine life largely undisturbed, and you can see fish freely moving around this construction site, and you can see a diver trying to do certain operations. And this picture brings it out even more clearly, where the diver is holding a concrete pipe and placing the concrete. So we can see that the amount of washout as far as cement is concerned is much less than you would expect, and we can still see a lot of fish in the region. Now, what is the formal definition of anti-washout concrete? This concrete can be placed underwater in a similar manner that normal concrete is placed in air. Initial development of this concrete took place in Germany, followed by extensive research and use in Japan. And this concrete uses a viscosity agent. In a normal concrete, we'll show how the concrete that we use in anti-washout concrete, we will see in a few slides, the concrete that we use for anti-washout concrete is more or less normal concrete, except for the fact that a certain amount of viscosity agent has been added to impart viscosity to address segregation and bleeding that may occur in a normal concrete underwater. Now these has other implications as well, as we shall see in this lecture a little bit and more so in the next lecture. Applications of such concretes include bonding and solidifying rocks and concrete blocks in shore protection works, underwater reinforced concrete for construction of wharfs, intake and discharge facilities for industrial plants, alternative for precast concrete for constructing breakwater, quay walls and so on, bridge foundations, minor fixing work and emergency repair works, maintenance works around underwater structures, construction and repair of shore protection, riverbed, water gate and so on. So anywhere we are trying to place concrete underwater, what we are not talking about here is whether the water is moving or not. That's a separate discussion. It's an important discussion, but we are leaving it out from our discussion for the time being. Anywhere the concrete is being placed underwater, we can use anti-washout underwater concrete. Now this picture showing normal mortar and underwater anti-washout mortar being placed in a measuring cylinder of water shows the picture as to how the underwater concrete or the anti-washout underwater concrete is so different from normal concrete. Normal concrete would involve this kind of segregation or a washout of cement particles or even fine sand particles from the mortar once it is dropped in water. This is not happening at all as far as this particular case is concerned, because this mortar has that viscosity agent that we talked about. So this viscosity agent imparts a certain amount of viscosity to the paste phase and therefore to the mortar phase and therefore to the concrete phase, which makes segregation extremely difficult. So since the segregation is difficult, certain other things follow, but that's what we are going to talk about momentarily and stick to that discussion even in the next class. Now here is the variation of the erosion proofness, whatever you call it. So since it's erosion proofness, a high value means high amount of erosion resistance. Here we are talking of low erosion resistance. So if we use very little viscosity agent, we obviously do not have any erosion resistance. The erosion proofness is 0. And if we increase it beyond this point, let's say, there is virtually no difference because we have already achieved a value close to 100%. There cannot be any more improvement. Now, therefore, as far as an engineering judgment is concerned, we are probably better off trying to use the dosage of the viscosity agent in the range of 1 to 1.5%, 1.3% and so on. So this becomes our standard dosage. Even though it's standard dosage, like any such discussion, this is highly dependent on the cement being used, the sand being used, their characteristics in terms of fineness, chemical composition and so on. And therefore, we always need to do laboratory tests to determine what would be an efficient dosage that we use as far as the viscosity agent is concerned to achieve the right amount or the desired amount of erosion proofness or segregation resistance. Here's another picture showing more or less the same thing. This is regular mortar and 2 is a mortar with a high dosage of the viscosity agent. This is 1.3% and this is, let's say, an economical dosage where it's 1%. So you can see a certain amount of turbidity that's lesser here, but if you're willing to live with this, yes, you can make do with 1% of the viscosity agent instead of going to 1.3. This obviously has not only implications in terms of segregation resistance, but also setting time and so on. So one must try to understand all the implications in designing that concrete mix, which includes the determination of the right dosage of the viscosity agent. As far as using underwater concrete is concerned, or the anti-washout concrete is concerned, the anti-washout concrete is more expensive as far as the material cost is concerned. There are reasons for it. More cement is used than in conventional concrete. The amount of coarse aggregate, which is the cheapest of the raw materials goes down. Therefore, the material cost indeed increases. Having said that, the construction cost or the concreting cost, which is the other part of construction, goes down drastically, and therefore the total cost of construction is still maybe 70%, 75% of the conventional construction costs. So that's how we can try to understand or get a better view of changes in the material cost and changes in the construction cost in making a final decision whether or not we should use the anti-washout concrete or go for conventional concrete. This here is a representation of the strength development in anti-washout concrete, and you can see here that the concrete is very much a normal concrete, a water cement ratio of 50%, 25 mm of maximum size aggregate, and we are talking of 28 day strength as usual. If we are using river gravel or crushed stone, made in air or made in water or made underwater, the strengths are not drastically different. They are just marginally different, and we can say that even if concrete specimens are collected underwater or in the air, the strength values will not be so drastically different. So we need to have this kind of backup data which has been collected for a particular site using a particular material by a particular contractor, so that the engineers have more confidence in going ahead and using a particular material. As I keep emphasizing, use of special concretes, use of special mixes places a lot more responsibility on the contractors and the builders, and even of course the clients who permit that use, in terms of quality control, in terms of developing the right specifications. Now this slide here draws our attention to some of the other things that we have left untouched as far as this discussion is concerned. One is that of still versus running water, self-compactability versus segregation resistance, methods of construction, for example tremies or buckets. Concrete always remains submerged. Now this condition must be specifically borne in mind because at certain times it has been reported that the drying shrinkage of underwater concrete or the anti-washout concrete is higher than normal concrete. That does not bother us so much simply because the concrete always remains submerged in water and the drying shrinkage does not come into play. So again, important to note that we must understand the environment in which the concrete is going to be when studying its properties or making an evaluation of those properties. There's nothing wrong in studying the property, there's nothing wrong in evaluating it, but keep that evaluation in the framework of the actual environment. Development and use of specially designed anti-washout concrete, that's something which we'll see in a greater detail in possibly the next lecture. This is just one example of the use of the anti-washout concrete. Now what we see here is concrete being used for a volume of 357-360 cubic meters with a required compressive strength of 18 MPa using 20 mm aggregate, slump flow of 40 centimeters, a water cement ratio of 51.3, and a unit water content of 205, with the viscosity agent given in terms of water percentage being 3.1 kgs per cubic meter. Now what it shows is that as far as the concrete is concerned, it's a very normal concrete from all points of view. The compressive strength, the water cement ratio, the maximum size of aggregate. Only thing is that the water content is slightly larger than normal concrete that we would expect in this day and age. Not only that, this is the water content after a certain amount of superplasticizer has been used. So this water content with the superplasticizer usage is what is the crux of the anti-washout underwater concrete. I'm leaving it to you to do as an assignment a study of the different proportions that are available. I'm going to show you one or two of them just now, but it is left to you to study some cases where this anti-washout underwater concrete has been used. This is yet another example where 246 cubic meters of concrete has been used with 21 MPa as the required strength, 40 mm aggregate, 60 centimeters slump flow, 54.7% of water cement ratio, and the water content being 208. And here we are talking of a viscosity agent at 1.2% of water, which turns out to be about 2.5 kgs per cubic meter. So the amount of viscosity agent is very small, but its effect is very, very significant as far as the properties of concrete are concerned. Now coming to the materials that are used in this concrete, normal blended cements, whatever you have, there's nothing special required for cement as far as use in the anti-washout underwater concrete is concerned. As far as admixtures are concerned, the viscosity agent, of course, is a special agent. It's mainly cellulose ethers, provide high amount of erosion resistance, and of course you use superplasticizers to reduce the water demand. And that's what I said, that when we are talking of 205 kgs of water, that is after we have used a certain amount of superplasticizers, then we need this much water. So you can imagine how much is the kind of cement content that is really going into this system. As far as proportioning is concerned, the dosage we've already discussed. Viscosity agent ranges from about 1 to 1.3%, and the dosage is adjusted according to the requirements, such as height of fall through water and the kind of characteristics of materials that we have. And as far as the consistency is concerned, in terms of the slump flow required, it could depend on the placing method, which could be pump, tremie or bucket, the placing condition of the concrete, whether it is slope, general condition of the layout there, reinforced or not reinforced, filling narrow spaces or that's not involved, deep spaces, and so on. So the placing condition and the placing method together, as usual, gives us the required kind of consistency which we want from the anti-washout concrete used. Recall that in the first case that we saw, we had a slump flow of only 40 centimeters, but in the second case the requirement was 60 centimeters. So the consistency in terms of slump flow could be quite different depending on the different conditions, depending on the different methods. This is the recommended consistency for anti-washout concrete under different conditions. For example, slope, simple shaped structures, reinforced concrete structures, filling narrow spaces, filling narrow and deep spaces. If you are buckets, tremies or concrete pumps, this is the kind of slump flows that you're talking about. So it could range from 25 to 60 or more, and 25 as a slump flow should be an interesting value for you because the geometry of the slump cone tells us that this diameter at the bottom is only 20 centimeters. That means a 25 or 30 centimeter kind of a slump flow is hardly any slump flow. That means the concrete hardly flows. These low values almost mean that the concrete doesn't flow. So it's just extremely viscous. Of course, when it comes to these larger values, there are some other issues involved. For example, if you increase the viscosity of the concrete, what are the other parameters that will come into play? Will it deform very quickly after you remove the slump cone? Just think about it, and I'll probably answer that question towards the end of this class if I don't answer it in another slide. Examples of mixed proportions. Here are two examples. A slump flow 45 to 55 centimeters. These are the strengths we're talking about, the air content we're talking about, water cement ratios. So this is the typical water content which pushes the cement content to these values, and the coarse aggregate content, let's say, is to these values because your S by A is not so very different. S by A governs the coarse aggregate to fine aggregate volumes in the concrete. So if the S by A is the same and we have pushed in a lot of paste in the system, the mortar volume obviously goes up because the total volume of coarse aggregate has gone down. That is something which is very, very interesting to observe and just see the amount of high range water reducers that have been used. So this exercise is an incomplete exercise. I'm just giving you the pointer, and I would like you to actually look up reports which talk about the mixed proportions used in some of the concrete projects where the anti-washout concrete has been used. As far as mixing is concerned, dry mixing may be initially carried out for about 30 seconds, followed by more mixing, more vigorous mixing, which could be 60 seconds or whatever it is after the water addition. With this, I more or less come to an end of the presentation today, which I told you will be a brief presentation. And this material, a lot of it has been communicated to me personally by my friends, and it should be used only for academic purposes and not anywhere else without express consent. This slide gives the suggested reading and references which you might find useful in following the material which has been presented today. However, this list is by no means exhaustive, and in fact it's for that reason that I've written list incomplete, and you are requested and encouraged to look at the internet, look for more relevant material, and try to understand the subject matter better. As far as something to think about is concerned, I've already mentioned a couple of things to you. Study the mixes reported in literature for anti-washout underwater concrete. Compare these mixes with normal concrete mixes in terms of the paste and mortar content and the size and grading of aggregate, both fine and coarse. And study the properties of anti-washout underwater concrete, especially in the fresh state, in terms of slump flow and parameters such as T500. Now, T500 is the time that the concrete takes to achieve a diameter of 500 mm in a slump flow test. So now, if the viscosity agent is not used, what is the kind of time that you would expect the concrete to get to a diameter of 500 mm? Recall that the initial diameter of the bottom of the slump cone is 20 centimeters or 200 mm. Now, for that diameter or for that concrete to spread to a diameter of 500 mm, how much time will it take with and without the viscosity agent? That is something which I am leaving it to you to think about, and not only think but also get some actual values from literature. Coming to an end of the discussion today, my gratitude once again to my teachers in Tokyo University, my friends in the corporate and academic world in India and Japan who have helped me understand this material, and of course to my students whose questions have helped me understand the material better. I look forward to seeing you again in another lecture where we'll continue our discussion on anti-washout underwater concrete. Thank you once again.